Let's talk air distribution and heating. So our HVAC system, heating, ventilation, and air conditioning, airflow is directed toward the windshield, dash, or floor vents, or a combination depending on the system settings. So if we're looking at our dashboard, here's our instrument panel right here. This is our steering column where our steering wheel would be. We have little actuators inside of what's called a plenum, or like a air pathway. You can see it this like tan color here. We have air doors that will help direct air in the directions that we want it. We have a blend door that blends the hot and cold air together to make the temperature that we are trying to achieve. And then we have a blower motor, a fan, that actually pulls air in and then blows it out through those vents for us. That airflow control, so multi-speed blower, is used to force air through the ductwork when the vehicle is moving at low speeds or to increase the airflow at any speed. Most systems use one or more flap doors that swing about 45 to 90 degrees. So in this case, we're seeing our evaporator core here. This would be our heater core. And what we're seeing right now is just the blend door. So it's choosing how much of that cold air and how much of that hot air are mixed together to give us the temperature we want. You can think of that like when you turn on a sink at home and you're trying to make it so the water's not so cold that you're freezing while trying to wash your hands, and not so hot that it's burning you. That ball valve, that mixing valve, is the same idea as this blend door. We're just blending the two temperatures together to come out with that Goldilocks situation just right. So air temperature control. Pretty much every system I've ever come in contact with is called a reheat system. So if we look at this, as far as airflow goes, with our little red lines there, we've got fresh air comes in, and we have also our recirculated air. So first we have to choose, do we want fresh air coming in or recirculated air? And then after we choose that, then there's a mix that goes on between, do we go through the evaporator first and chill the air down and condition it, or do we bypass the evaporator altogether and just go through the heater core? Most vehicles, like I said, are set up in what's called a reheat system. So as far as the manufacturer is concerned, they'd like the AC to be running all the time. Air conditioning systems don't just chill the air, they also help remove dust, pollen, foul odors, moisture, all from the air. Think about how an AC unit always drips a little bit of water out of it because of the condensation. Well, that condensation that builds up on an evaporator helps catch dust and other debris, and then as the water droplets get large enough to start dripping and falling off of the evaporator, well, then they also bring all those little pollutants along with them. And also, as humans, we like it when the air is not super humid, right? We're always like, it's not the heat, it's the humidity. Well, yeah, here we go. So most systems are that reheat method, but that doesn't always do anything. Like whenever my car tries to automatically turn the AC on, I'm like, no, I want that extra 2 miles per gallon, so I turn it back off again. But that's totally up to the passenger. One other way of filtering the air is with cabin air filters. So we have an engine air filter that filters the air going into the intake manifold and into the engine. We also have cabin air filters, which are very common on vehicles, and these filter the air coming into the passenger compartment. They'll catch things like dust and debris and smells from exhaust and all that kind of stuff. They'll also catch like little bits of leaves and other bits of debris like that as well. They tend to get dirty pretty quickly. They have like a 15,000 mile replacement rotation, and usually when you pull one of those out, they look pretty nasty. And the reason for that is twofold. One is a lot of them come in a gray color to begin with because they have what's called activated charcoal inside of them, and that charcoal absorbs odors and other nasty little chemicals and things like that. So that gray color comes from the fact that there is charcoal in the filter to begin with. And second of all, they ionize the filter, which just means that the filter, because the way that it's made, the like structure of the weave and the material it's made out of, it tends to build up static electricity, which tends to pull things towards it, like hair and pollen and dust and stuff like that. So and we also have a lot of air flowing through this filter, because with the blower motor turned on, it's actually sucking air pretty hard. Could be under the hood, which this lower one here for sure is an under the hood one. You can see it's caught all kinds of pine needles and nasty stuff. Or it could be in the glove compartment, which is more similar to what this style is. You see how it's got like a little tray built into it. The glove compartment ones still get pretty dirty, but they don't seem to catch as much of the debris. You have to be careful with air filters like this, because when you pull them out, it's sitting right above the blower motor, so any debris that doesn't come out with the filter could fall down into the blower motor. If that happens, I've had good luck with just turning the blower motor on with the air filter removed and, all the stuff out of the way. It tends to cough the stuff out. Otherwise, you'll hear it in there flapping around, and a customer's going to be pretty grumpy about that. There's our plenum. So this is sitting inside the vehicle. This would be up, the seal up where fresh air comes in. Here are the lines where my refrigeration and refrigerant would get pumped through to the evaporator. Here's where the hot engine coolant would come in for the heater core. So this is all facing the front of the vehicle. It's kind of oriented in a weird way. Here's the blower motor, which is usually pointed down towards the floor underneath the glove box. And then I think this is an actually important thing to mention, is this condensate drain. When we're running the AC, we're going to be building up condensation on the evaporator. That means moisture is going to be building up in the bottom of this plenum. So we need a drain, because otherwise the water would become stagnant, and like mold and mildew would grow in it and start to smell yucky. So having a drain is very important so that the water can drain out. It's not uncommon for this drain to have a little flapper valve, a little one-way valve in it, so that water can flow out, and so that things like mice or other pests can't crawl up into the dashboard and make a little home in there, which would be a bummer. We have the plenum and control doors. We have the ducts themselves, which is how the air flows through, like the pipelines. We have the doors that control the motion of that air. We have an inlet door, also called fresh air, recirculation, or outside air door. And that's how we choose whether we want to pull in fresh air or if we want to recycle the air that's already in the vehicle. Let's think about those cold mornings or those really, really hot afternoons in the summertime. We tend to like to reuse the air that's already been treated, so it's already been heated up a little bit, so it's easier to heat it up even more. It's already been cooled down a little bit, so it's easier to cool down a little bit more. Or if we're driving past a farm that they're putting down fertilizer, and we don't want to smell the nice odors, so we close the door, hoping that that'll make things a little bit better. Our temperature blend door, other names for it there: air mix, temperature door, blend door, diverter door, bypass door. That's what gives us our mixture of hot and cold air. And then usually we're going to end up with three pathways: defrost towards the front glass, windshield, vents towards our upper body, and then we have the floor vents down towards our feet. Most systems are made to fail in the defrost position so that the ice can be removed from the windshield. Seems like a good way to fail. Here we have a good look at our reheat system. No matter what air comes in, it has to pass through the evaporator first, which is just a little radiator inside the dashboard. And then depending on our blend door, we can either have full AC coming out, right? No, the heater core doesn't heat anything up. We can have full heat, so it's been conditioned, right? We've removed moisture and any kind of debris maybe from it, any pollens, irritants. It then gets fully heated by the heater core and then can go out to whatever duct we choose. Or maybe we've been driving for a little while and we don't need full heat anymore. The cabin's warmed up enough so that we can do a nice mixture of the two. Now the evaporator is pretty easy to control what the temperature is of it. It's either pretty close to 32 when the AC system is running and the compressor is being spun by the belt, or it's pretty much ambient temperature because that's what's getting blown across it, and nothing is, no refrigerants flowing through it at the time to keep it cooled down. So that's the state that these are in most of the time, honestly. And then in this system, we've got another look. Here's our reheat system. Here's another reheat system, but this one has a blend door. And this one, and BMW was really big on this for a long time, and some other manufacturers have tried different versions of it as well. But BMW went full on. They put a little electronic control valve in the coolant hose going to the heater core. And if they didn't want the heater core to heat the air up, they would just close the valve, stop any hot coolant from going through the heater core, and the air rushing through would eventually change the heater core to whatever temperature the air coming into the vehicle was. And so that way we'd get better cooling, because in this system I've got, let's say the AC is on. This is on full, as cold as it gets, somewhere around 32, so that the water on it is just about to freeze but not quite frozen yet. Air passes through it, bypasses the heater core, but there's still this like hot spot inside the plenum which, heats up some of the air as it goes by. In this case, if we can shut it off so that this never comes up to temperature and we have our nice cold air coming through our evaporator, well, then it's going to be as cold as possible inside the vehicle. So just two different takes on a similar concept. A little look at some of the ducts placed in different places. These are there for our passengers in the back of the vehicle. There's usually ducting in the center console for the poor saps in the back that are all frozen or sweating, right? Some vehicles, these are older ones obviously, but some vehicles use non-electronic means of controlling these doors. So in this case you can see a vacuum actuated system. The control valve or control knobs on the dashboard would hook up different pipelines to vacuum, which was coming out of our engine, right? The intake manifold has a nice vacuum supply. So they're just using that vacuum to, when they'd put it here, it would pull the little actuator arm towards it, and then when we would exhaust the vacuum from it, there's a little spring inside that would allow it to return back to its normal spot. This is a look at what a vacuum diagram would look like for a vehicle. You can see all the heavy hitters are there. We got the blower motor, our evaporator, our heater core. And the interesting thing is, even in those systems, the blend door was usually electrically controlled because it needed to have more than two states. It couldn't just be on or off. It needed to be able to be fully cold, medium cold, kind of warm, super duper warm, right? Other vehicles have these cable actuated systems. These were mostly found in economy vehicles, so like you might find it in an old Ford Focus or a Honda Civic, something like that. Electronic HVAC controls. I'm just going to hop right into it. The simplest one is a 2-wire, so it's just a DC motor, just like a power window or power seat or door lock, or all DC motors. And we would just choose our polarity based on which way we wanted the motor to spin. Now these work perfectly well. The issue is that we don't really ever know what position the motor is in. So this is usually for like a fully on, fully off type situation, like a fresh air door. I either want fresh air to come in or I want to recirculate. What the module does is it just goes towards the fresh air side for a few seconds until it knows, like, okay, I definitely have made it there. And then when we want it to recirculate, it just switches the polarity to spin the motor towards the recirculate position, and it just counts a few seconds until it's there. Pretty much all that this is good for is just those two positions. If we try to try to split the difference, the motor's going to get lost because we have no idea what the position is. And there's also the potential to maybe strip out some of the internal gears if we leave it on in one way for too long. So you'll see recirculation doors are pretty prone to stripping out the gears. You get like a heinous little clicking noise out of them as they're trying to work. Then they started to make the motors themselves, the little door actuators, modules of their own. And so it would send signal back to a potentiometer, or actually as we changed our HVAC control, a potentiometer would change the voltage. It would interpret that signal and place the motor in the right spot. That works perfectly fine. It just makes each one of these actuators really expensive, and it makes our HVAC control just like a bunch of switches and resistors. So the thing that's easy to get to is cheap. The thing that's hard to get to is expensive. So double expensive because it's hard to get to and it costs a lot. But pretty much everybody's gone to at this point is a motor with a potentiometer inside of it. The potentiometer, as the motor moves along its travel, this little wiper moves along the resistor, and that signal that feeds back to the module lets the module know where the motor actually is. So it can tell, you start the vehicle up, it looks at where all these actuators are set at, it looks at what's set on the HVAC control, which is now a module, it's a computer in its own right, and it can make small little adjustments to make sure that everything's where it needs to be. It even makes it so that we can have automatic temperature control, so I can set my car to 72 degrees, and that little blend door might be moving around all over the place as I'm driving, trying to keep me at the temperature I want. Bone cold in the morning, that thing's wide open, letting all the heat possible in. I've been driving for 20 minutes, the car started to warm up. Maybe it's somewhere in the middle now at that point. Shows major portions of the plenum, which is our air inlet section with the air inlet fresh air door and the blower motor. We have our plenum section, which houses the heater core and evaporator cores to give us our temperature control. And then we have our air distribution section, which actually directs the air in the proper direction. Do I want it at my face? Do I want it at my face and my feet? Do I want it at my feet? Do I want it at my feet in the defrost? Do I want it just defrost? Right, we've all used that stuff before. This is what those actuators look like on the outside of a plenum. Granted, this plenum's been removed from the vehicle, but you can see your little electrical connector there. Here's where the little motor lives. And then here's the little gearing that goes into the actual ducting. And in the ducting is the door. So this actually has to line up with the door in the right way. And then once it's keyed in right, you can bolt it in place, and then the motor and the gearing will flap the door back and forth. For our blower motor, we could have a blower motor, we just turn it on or off. But when a blower motor is turned to high, it's pretty noisy and it's also blowing pretty hard. So it's not the most comfortable situation unless you're really hot or really cold and you're willing to give up those conveniences to become the right temperature, which we've all been there before. What they what they always do is there's some sort of a blower speed controller. This is an electronic version of one here, but there are also old electrical ones as well. They just have little resistors in them that drop part of the voltage. Let's see if we can find one of those. Here we go. So here's a blower resistor. Depending on what speed I put my switch at, say I want high speed, it just allows, we'll go from power. Here's power through my relay, comes through, and through high speed it can go directly to ground. We don't go through any of these resistors, so it gets all the voltage, and there's a fair amount of current that's able to flow through that circuit. As soon as I want to drop down one from that high speed, let's do medium high, I come through my relay, through my motor. I can't go this way because I'm no longer connected, right? That's open. So now the current's going to flow through the blower motor resistor assembly, and it goes through, in this case, one resistor to line up with that medium high speed. goes through the ground. And so now one of these resistors has dropped some of my voltage. So this doesn't get all 14 volts off of the battery, and it also is raising the resistance of the circuit, so there's less current flowing as well. If we think back to wattage, wattage is how much work a circuit can do. Well, if my voltage is reduced and my amperage is reduced, then I get less wattage, because wattage is determined by multiplying voltage and amperage. So less of each makes less wattage. Let's do the medium low now, I guess. Why not? In this case, we come through our relay, through the motor, go through one resistor 2 to come to medium low, and then we'll be able to flow through to ground. And then at the lowest speed, go through 1, 2, 3, and I just go through ground. You see how the switch is just like not doing anything. All 3 resistors drop parts of the voltage, so at this point we're down to like 9 or 10 volts probably left for the blower motor, and way less current flow going through it as well. So less wattage, and if the job that the blower motor is trying to do is spin fast and blow air, then it's going to do less of that. Here's a diagram showing my actuators. So here's my blower motor actuator right here. So the HVAC control module changes polarity depending on which way it wants the actuator to move. And then it gets feedback on this wiper signal wire feedback. As it moves, this wiper mechanically moves across the resistor, and the voltage that is received at the module changes, and it's able to interpret those different voltages as what position the door is placed in. This would be a blower motor circuit that has a solid state controller. So instead of using resistors, this gets sent a signal from the HVAC module, variable blower control. This sends out its own little signal, and the internal workings of this work to limit current flow through the motor. So if you think about duty cycle, which is percentage of on time, the way that this works is there's just less and less percentage of on time as the motor spins slower and slower. 100% on time for high speed, 75% on time. So like, let's say every second, this thing is pulsing 100 times. So out of those 100 pulses, it chose to be on 75 of those 100 pulses, gives us 3/4 speed. And believe me, we'll work on this a little bit in person. It's a little easier that way. Our cooling system is the source of heat in the vehicle. We're going to talk about refrigeration later. So coolant flows through the engine where it picks up heat. It's picking up heat to try to keep my combustion chamber at the right temperature consistently, so we have great combustion every single time. But as much as 2/3 of the energy from fuel can be wasted as heat. And so we're trying to figure out ways to use this heat to do other stuff, so we're not wasting as much of our fuel energy. And one easy way to do that is take that hot coolant, send it through a radiator in the dashboard, and heat the air up so that we're not shivering. Combustion temperature on a gasoline vehicle is somewhere around 4,500 degrees. You can see my little coolant jackets around the combustion chamber, and then also the cylinder at large. So those are trying to soak up and sap away that heat as quickly as possible. Exhaust gas temperatures are still as high as 1,500 degrees, so there's more than enough heat to go around here. Most of this stuff gets lost right off to the atmosphere through the radiator in the front, the metal of the engine, and also the exhaust coming out the back of the vehicle. Coolant flow rate, maybe this is obviously not a standard, it's just like giving you an idea. But coolant flow rate through the engine could be as high as 1 gallon per minute for every 4 liters. 1 gallon per minute for each horsepower the engine produces. So if like a lot of modern vehicles are up around 150 to 200 just for your commuter. So let's call it 100 horsepower. That means that's 100 gallons per minute going through the engine. That's a pretty incredible amount of coolant flowing through an engine. But when we see how much heat is being produced, we start to understand why it needs to be rushing so quickly. So hot coolant comes out the thermostat housing on the top of the engine. Engine coolant outlet is connected to the top radiator by the hose. The hot coolant, as it goes through the radiator, cools and becomes denser, so it wants to flow downward because it physically weighs more by volume. And then that can be pulled back in through the thermostat and into the water pump assembly at that point to be recirculated. When the engine's cold, the thermostat stays closed, and the engine just keeps recirculating its own coolant over and over again to try to warm it up so that the engine can come to operating temperature as quickly as possible. That's around 70 degrees Fahrenheit, and that's when most of our emission stuff works the best. Our oxygen sensors are paying attention to the exhaust stream and helping us control fuel timing. Our EGR systems working properly, evaporative emissions can come on. So we're trying to get up to operating temperature in as little amount of time as possible. Once we start to come to operating temperature, then there's a wax pellet inside the thermostat that allows the thermostat to open, and then coolant can bypass to the radiator, at which either ram air, just the wind from us moving down the street, or the cooling fans can pull air through the radiator and help cool the coolant off. Thermostat opening temperature, early opening is somewhere between 170 and 190 degrees Fahrenheit, and then fully open is going to be around 210, because when we're up to full operating temperature, right, 70 degrees was emissions compliant stuff starts happening, but the engine's actually at operating temperature as far as best combustion quality goes at somewhere around 190 to 210 degrees Fahrenheit. Anything colder than that, we're not going to get full combustion. Anything hotter than that, then we might start to create some gases like oxides of nitrogen that we don't want, or maybe even then start damaging the engine as the piston starts getting too hot and swells up bigger than the whole of the cylinder. There's our little radiator. So cross flow radiator, so we have these tanks on either side. Here's my inlet tank. See the little upper radiator hose would go there. The coolant fills that tank and then flows across these tubes to my other tank with the outlet down at the bottom. And the fan really only comes on when we have our air conditioning on, always, but then also if we come to a stop and we need help cooling down the engine coolant, the fan draws air through the radiator. Otherwise, once you're up around 15 or 20 miles per hour, there's so much air passing through that radiator, the fan doesn't really need to do that much work. The heater core, there's a nice little look at it inside. This is underneath the dashboard, inside the passenger compartment of the vehicle. These two hoses here, or tubes, would be poking up into the engine compartment. So this is how hot coolant is able to circulate. And this just looks like a radiator, but just a much smaller one. If we have a leak, lots of techs like to use dye because it can help you more quickly see little leaks. Usually we go through and clean off any residual coolant. Then you put the dye in the system, let it run. Definitely let the vehicle come up to temperature, and with a black light and those special yellow glasses, you go around and look. And you're trying to see there's usually like a fluorescent greenish color of the dye, and you're trying to see where it's coming from before there's so much coolant coming from that spot that it's hard to actually pinpoint, like, is it where the hose meets the piece of metal, or does the piece of metal maybe have a crack in it, and that's why the coolant's able to leak out past it. This is showing one of those control valves we talked about earlier. Close the control valve and that eliminates the heater core from the circuit. No longer will anything pass through it. It's full of coolant still, but because it's not being refreshed with hot coolant, it'll eventually lower its temperature down to whatever ambient temperature is inside of the plenum. And then heater diagnosis. The major things are, is there enough coolant in the vehicle? You'd be so surprised how many times people come in and say, I have no heat, and it's because the coolant level's low. The reservoir and the heater core are the two highest points in the system. So the first place in the system to get an air pocket in it's going to be the heater core. So someone's got a leak, maybe they got a leaky radiator or a hose or something. They haven't started overheating the engine yet, thank goodness, but they're starting to not get as much heat out of the vents. So is the coolant level any good? Then what runs the water pump? Oh, a belt. Is the condition of that belt in any good shape? Let's take a look at the radiator in the front. Make sure that it doesn't look like things are kinked, or there's no leaks, or there's not a whole bunch of debris all stuck up on it. I've also seen ones that were so corroded that air couldn't pass through them anymore, and so we were getting overheating issues because of that. We're looking for clogs, any restrictions, and heater cores are prone to clogging because the inside of a cooling system is pretty corrosive. When coolant is new and mixed properly, it's not corrosive. That's why we have to put the right coolant in the right vehicle. But after around 30 to 60,000 miles, or up to now, they say that they're good for up to 100,000 miles at this point, coolants start to chemically change. And all the heat and the crazy stresses inside of an engine start to create the same conditions that rust happens in, electrolysis. There's actually electrical current passing through the block of the engine. Anything that's case grounded on the engine is doing that. And so all that stuff kind of can build up to a cooling system that's prone to creating this like white, chalky substance basically as the aluminum of the engine breaks down. And then that can, even if it gets in with cast iron, can start to turn like a muddy or sludgy color. But the heater core is the smaller of the two radiators on the system, and that one clogs up before the actual main radiator. Granted, the main radiator can clog up as well. So you want to make sure that if you're going after a vehicle heat issue, that you don't forget that you might need to flush out that heater core. A lot of people are surprised that you really shouldn't have more than a 5-degree difference between the two hoses going to the heater core. You think, oh, it goes in, it has air blow through it, the air takes on the heat, the heater core should be much cooler. 5 degrees is the difference. So in this case, we're seeing 150 to 6 degrees Fahrenheit on one hose. That must have been the return hose, because the coolant going to the heater core should have been somewhere around 180, 190 degrees. So that's definitely more than a 5-degree difference, and what that shows is that the heater core is probably clogged up, making it so that not as much coolant can flow through it, which means the coolant that does flow through the heater core loses more of its heat. Testing the pH to see if maybe the coolant is at a basic or alkaline state that is enough to start to cause rust. So that'd be a telltale. That's what this tech is trying to find, but it doesn't seem like anything weird's happened. Looking at the freeze protection to see if it's been mixed with the right amount of water. Seems normal. It goes about flushing the heater core by passing, usually a garden hose and a couple of adapters is enough to flush the heater core out. And putting water in, water's coming out. That's usually a good sign. It doesn't look like it's just trickling. So it goes both ways, right? You want to back flush the heater core because all the material is getting forced one way through it all the time. So you're likely to get most of it out by going the opposite way, but usually we'll flush both ways. Didn't seem to work, so now he's got to go and put a new heater core in it. So the whole dash comes out. The AC refrigeration needs to be recovered because when we pull the air distribution box out of the vehicle, the evaporator's coming with it. So we want to make sure that there's no refrigeration in there, or no refrigerant in there, because that'll cause a really big issue. We pull back, you can see the heater core. goes and tests the heater core out of the vehicle, because this person must be hourly and not flat rate. But they're testing it and they're able to see that there are hot and cold spots in it, so it's definitely plugged up. While you're in there, because you had to pull the whole dashboard out, it's not uncommon to sell an evaporator at the same time as a preventative issue. You can see on this evaporator where there are these dark spots that might denote that some refrigerant was leaking due to corrosion. From those spots as well, the refrigerant pulls an oil through the system with it, and so these like oily spots are telltale signs that there's been a leak in those spots. Probably a very, very small one, but a leak nonetheless. Replacement components don't always look the exact same, but they should have the same dimensions. So just a good point there. Gets it all back together, and they must have used a Sawzall or something to cut one of the tanks off the side, and so you can see how water's only passing through a very few of those crossover tubes. So a lot of this heater core is clogged, and that's why the customer had the complaint. All right, crash course through heating and ventilation, but well done, and I'll see you next time.